have been developed different algorithms for fog and haze removal. The most common reason is road accident generally happen due to the bad weather condition. So that's why nowadays many researchers are trying to develop such kind of algorithm which will work for that real-time implementation. So that is our motive. So that is our motivation for our work, real-time implementation. As we all of know, imaging in poor bad weather condition is generally degraded by bad weather particles. So depends on that bad weather particle, which is broadly classified into two categories. One is steady bad weather condition and other is dynamic bad weather condition. So in steady bad weather condition, examples are fog and haze, and dynamic bad weather conditions, examples are rain and snow. So we are focusing on that steady bad weather condition where floats are steadily float in the air. So this is the image degradation model which is useful for bad weather condition. You can just enter it. So the primary cause for bad weather, for degrading the image, two factors are important. One is attenuation and other is air light. So we want to capture that object in the presence of bad weather condition. So here this is object and the camera. The reflected light beam coming from an object to the camera is called direct light. Yeah, but this direct light gets attenuated due to the presence of this fog and haze particle. So this is one of the cause for degrading the image quality. And other is some amount of light coming from an environmental illumination is scattered due to the presence of atmospheric particle and scattered towards the camera, which leads the color differentiation and added the whiteness of the more whiteness in the image. So these two factors are highly degraded the image quality. So this is the enter it. No, next right. So this is the mathematical formula which is useful, which we will use for bad weather condition. This is the input I of x is the observed intensity. So we have haze image or foggy image, and this j of x is the output image, or we can say dehazed image, defoggy image. And then we have two unknown parameter. One is air light and other is t of x. T of x is the distance between that camera and that object, and a is the air light, which I have already discussed in the previous slide. So if we will calculate t of x and a, then we can get our recovered scene radiance. So these are our methodology for proposed work. First obtain hazy image, then obtain dark channel prior method, then estimate air light using the dark channel prior method, then estimate the transmission map using dark channel prior method and fast Fourier transform method, and then finally we can get our result j of x. So this is the flow chart for haze and fog removal algorithm. So this is, we have one input images, we can say in a dense haze images or foggy images. So first we calculate the dark channel prior for this input images. Then we apply our fast Fourier algorithm for the dark channel. And then we calculated the atmospheric light. And then finally we estimated the transmission map. After calculating the transmission map, we can get the scene radiance. So this one is the fast Fourier transform result. This one is the refined transmission map. Here we use median filter also for smoothing the result. And this one is the output image. So we can easily see that here we can get very good result after applying these methods. So next slide. First of all, what is dark channel prior? So in most of the non-sky patches, at least one color channel has very low intensity at some pixels. It means that in that patches, what we are doing, in that images, we are taking patches in 3 into 3. And then we are finding out that minimum of that patches. So minimum of this one, So we are taking 3 into 3, and then minimum of that RGB component, which component has less pixel intensity, that one is our dark channel prior method. So here even in clear day, we have some database. So even in clear day, some dark pixel must be there in that images here. But in presence of fog, in that dark pixels contain some whiteness also, because air light introduce some whiteness, in that additive whiteness we can say. So in hazy images or foggy images, we have dark pixels with whiteness here also. So what we are doing, the next, this is dark channel prior method, and next we are taking most haze opaque part. So we are taking 0.1 brightest pixels which is present in the dark pixels, because some dark pixel contains some whiteness also. So that whiteness is our air light. And then back. So the pixel with highest intensity is our dark channel, is our atmospheric light in that patches. Then we estimated the transmission map using dark pixels, dark channel prior method and fast Fourier transform. Generally, when we are applying, we are talking about patch dark pixel. Some block artifacts must be there in that images. So what we are doing is, because of that blocks, some high frequency noises must be there in that transmission map. So we are using fast Fourier transform method. For first we calculated high frequency and then low frequency for the dark channel prior method using high pass filter and low pass filter, then combined it and then refine this transmission map using median filter. Then finally we can get our refined transmission map by using this dark channel prior method and FFT based method. Then we have this A and T of X, then we can recover our J of X. So this is the final recovered scene radiance. So this is the formula for this, which I have already discussed in the previous slide. Then these are the experimental results. So here's number of samples. We have taken almost 200 samples. Here we are, but we are focusing on this image because dense haze is present in that image, and recovered image is very clearer. Even in quantitatively, we can say that the quality of this image is good. And the next slide, we compare our output result using bilateral filter method. Existing method is bilateral filtering method. We are getting same result. Even output image result, quantitative, it's the same. But what is the difference? How we will, why we are comparing with this bilateral filter? Next slide. So. Okay, then for performance matrix for quantitative analysis, we use blind assessment method, and then parameter missing here. So E and R. E is our number of visible edges which is present in that in the recovered image, and R is the average gradient. If E and R is high, then we can get better result, better dehazing result. So E is our number of visible edges and R is, so we have considered three parameters. One is E, R and processing time for quantitative analysis. So this is the simulation and result, algorithm, processing result, proposed method. E and R is this, and then processing time. R processing time is 0.8 for sample 1. Processing time is also, we know ki it depends upon processor, image size itself. So these are the seconds time complexity of that image, 0.5 to 8, and these are the E values. And then next slide is the bilateral filter. This is the processing time by using bilateral filter, E and R. So we are getting comparable result when we are comparing with bilateral filtering. But the thing is that what is the main advantages we proposed? What is the advantages? Next slide. So here we process them using MATLAB, and this our processor is this. Size is this. Bilateral filtering for sample 4 is taking almost 78.944% processing time, and our method is taking 3.534. So if we are considering only sample 4, our improvement is 95.52%. Overall improvement is 88% compared with bilateral filtering, because generally bilateral filtering is using for removing the noise from the images. So that's why this one is a popular existing method for foggy and hazy images. So that's why we are compared with this bilateral filtering method. So conclusion is this approach is giving a better result with speed improvement, and it is taking only 88% of the time as compared with the bilateral filtering. So advantages is we are reducing till 88%. We are focusing on mostly real-time processing kind of thing. At the same time, visibility of that image is also good. So here improvement with 88%. We are also trying with the next is a hardware implementation for that work. And then references. These are the references which we all the references, and thank you.
Any question?
Ma'am, it's actually that we know some dark channel, it means dark pixel must be there, like in 00114. So we are trying to calculate that dark pixels value, which contains also whiteness of that image. So if the minimum of that pixels, in that patch, how much intensity? Yeah, intensity is. If a minimum intensity, then that one is
What are the disadvantages of that?
Sir, I will check for that, because some of the disadvantages must be there, because we can't say but advantages is real time based. Okay, we are 88%, so we are trying for that hardware implementation. If it will work, then we'll see what some of disadvantage, but I didn't check, so we can't say that is it.
Thank you.
Now I request Rahul Patel from IIT Roorkee. He is not present. IIT Roorkee from